Okay, let's go. Number 1. The star that is older than the universe. In 2000, astronomers pointed the Hubble Space Telescope at a dim, fast-moving star in the constellation Libra and measured its age. The result was published quietly, without fanfare, in the Astrophysical Journal. HD 140283, nicknamed the Methuselah star, is 14.4 to 6 billion years old. The universe is 13.8 billion years old. A star cannot be older than everything that exists, and yet, HD 140283 was first catalogued in 1912. Its unusual velocity of 200 miles per second already marked it as a relic, moving too fast for anything born recently. Howard Bond of Pennsylvania State University led the definitive age study, published in the Astrophysical Journal Letters in 2013. The star sits 190 light-years from Earth in the constellation Libra, moving so fast it will escape the Milky Way entirely within a billion years. Its chemical composition identifies it as a population II star formed from the primordial gas of the very early universe, containing almost no elements heavier than helium. Spectroscopic analysis detected uranium and thorium in its atmosphere, radioactive elements whose decay rates allow precise age calculations through a technique called nucleocosmochronometry. The 2013 measurement yielded 14.4 to 6 billion years, with error bars of plus or minus 800 million years. The minimum age falls at 13.6 to 6 billion years, fractionally below the universe's accepted age of 13.8 billion. Astronomer Brian Chaboyer of Dartmouth, who helped develop the stellar aging technique, acknowledged the tension between stellar ages and cosmological models is real and has not decreased with successive refinements. Dozens of similarly ancient population, two stars occupy the galactic halo, the oldest structural region of the Milky Way, with several carrying age estimates that resist reconciliation with the standard timeline even under generous assumptions. Mainstream cosmology says the error bars save the standard model. The minimum age of 13.6 to 6 billion years technically falls just below the universe's 13.8 billion year age. Uncertainty in the Hubble constant, the number governing how old the universe is, also shifts both figures. Refine the measurements further, the argument goes, and the paradox dissolves. The Methuselah star is a known problem under active investigation, but the central estimate has not moved. Every refinement since 2013 keeps HD 140283 above 14 billion years. Chaboyer has written that the discrepancy is not narrowing. HD 140283 is not alone. Dozens of population, two stars in the galactic halo carry ages that resist reconciliation, and the ensemble is more troubling than any single star. In 2023, University of Ottawa astronomer Rajendra Gupta published a paper in the monthly notices of the Royal Astronomical Society arguing that when evolved coupling constants and tired light models are incorporated, the universe may be 26.7 billion years old, more than twice the figure taught in every introductory cosmology course. The paper received brief coverage, then silence. What the mainstream does not say plainly is this. If HD 140283 is older than its minimum error bound, the standard cosmological model is not incomplete. It is wrong. Either the universe is older than 13.8 billion years, or stellar aging models carry systematic errors no one has identified, or physics operated differently in the early universe than any current theory predicts. All three options require rebuilding assumptions that cosmology has treated as settled for decades. The star was born from something. Before the Big Bang, cosmology says there was nothing, no space, no time, no prior state. But HD 140283 carries the chemical signature of a something that existed before the universe we measure. Its existence doesn't just challenge a number. It challenges whether the Big Bang was the origin of time itself, or merely a transition between conditions we don't yet know how to describe. From here, a single star challenging the universe's age. We zoom into what happens when time is measured not at cosmic scales, but by the technology in your pocket. What if the Big Bang was not the beginning of time, but only the beginning of our current epoch? Why has no major NASA press release discussed HD 140283 in the decade since Bond's paper? And if a star predates the universe that supposedly gave birth to it, what does it mean to say the universe has an age at all? Number 2. The clocks that prove you are aging at the wrong speed. Your phone knows something disturbing about the nature of time. Without a correction applied continuously by ground stations, your GPS would drift by 7 miles every single day. Not because of satellite orbits. Not because of signal interference. Because time itself runs faster in orbit than it does on the surface of the Earth. NASA has known this since 1971, when physicists Joseph Hafele and Richard Keating flew atomic clocks around the world on commercial aircraft and watched them come back slow by exactly as much as Einstein's equations predicted. They published the result in Science that year. No press conference, no public briefing, a footnote in the literature, and time kept running unevenly while no one said how far the implications go. Hafele and Keating's 1971 experiment confirmed both special and general relativistic time dilation to within 10% of theoretical prediction. GPS satellites orbit at 12,500 miles altitude, traveling at 8,700 miles per hour. Gravitational time dilation. The slowing of time in stronger gravity causes GPS clocks to run 45 microseconds per day faster than surface clocks. Velocity time dilation from orbital speed causes them to run 7 microseconds per day slower. Net result? Ground stations apply a continuous correction of plus 38 microseconds per day. Without it, GPS error accumulates at 7 miles daily, enough to make every navigation system on Earth functionally useless within weeks. NASA astronaut Scott Kelly spent 340 days on the International Space Station from 2015 to 2016. Upon return, Kelly was measured as 5 milliseconds younger than his identical twin brother Mark, who remained on Earth. Beyond the clock, biological differences accumulated. Kelly's telomere lengths briefly extended, then contracted, and gene expression patterns diverged measurably from his twins. NASA's twin study results were published across 11 coordinated papers in Science in April 2019. The Event Horizon Telescope imaged Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy, producing the first direct image in 2022. Mainstream physics treats time dilation as solved and well documented. The corrections are automatic. Scott Kelly's 5 extra milliseconds of youth are a curiosity. The twin study is cited as evidence that human biology can withstand long-duration spaceflight. Nothing to see, but here is what the press releases don't include. Near a stellar mass black hole, 1 hour inside the event horizon equals 7 years outside. Near a supermassive black hole, the ratio stretches to centuries passing outside for each moment experienced within. Sagittarius A star, 4 million times the mass of our Sun, sits 26,000 light-years from Earth at the center of the Milky Way. The Event Horizon Telescope team published extraordinary measurements of its photon ring and accretion disk temperatures. What appears nowhere in public-facing releases is the full calculation of what time dilation means for matter currently falling towards Sagittarius A star. From our reference frame on Earth, that matter is not falling in. It is frozen at the event horizon, suspended at the boundary between time and timelessness. Every star, every gas cloud, every particle that has ever approached the galactic center's black hole is still there, stretched across the horizon in our reference frame, because time has stopped for it. The entire future history of our universe will play out before that matter crosses the threshold. We sit in a galaxy whose center contains a machine that stops time, and the scientific community discusses this in terms of gravitational lensing and plasma temperatures. From the frozen boundary of our galaxy's central black hole, we travel outward to the largest scale of all, and find that the primary ruler of cosmology is giving 2 different answers. If time runs faster in lower gravity, does it flow differently across the vast voids between galaxy clusters? What would full disclosure of time dilation calculations near Sagittarius A star reveal about the nature of the present moment for objects at its horizon? And if parts of our own galaxy exist in a region of stopped time, what does the word now mean? Number 3. The universe is expanding at 2 different speeds, and physics cannot explain why. 2 numbers, both measured with Nobel Prize level instruments, both supposedly measuring the same thing. They disagree by 9%. And in cosmology, 9% is not a rounding error. In cosmology, 9% is the difference between two completely different universes. One team measures how fast the universe is expanding by reading the oldest light in existence. Another team measures it by watching nearby stars die. They get 67.4 and 73.4 kilometers per second per megaparsec, respectively. The gap between those two numbers is called the Hubble tension. What it should be called is the moment cosmology stopped being able to claim it understands the universe. The Hubble constant, named for Edwin Hubble, who first measured cosmic expansion in 1929, describes how fast space is stretching between galaxies. The European Space Agency's Planck satellite mapped the cosmic microwave background in 2013 and 2018, yielding 67.4 kilometers per second per megaparsec with high precision. The SH0ES team, led by Adam Riess of Johns Hopkins University, used the Hubble Space Telescope to calibrate Cepheid variable stars and Type 1a supernovae in the nearby universe, yielding 73.4 kilometers per second per megaparsec. In 2023, the James Webb Space Telescope confirmed the SH0ES measurement independently, eliminating instrumental error as an explanation for the gap. The discrepancy has grown from a 2.5 sigma statistical tension in 2013 to a 5 sigma conflict in 2023. In particle physics, a 5 sigma result is the threshold for claiming discovery of new physics. Multiple independent measurement approaches consistently cluster around one of the two values, and never in between. Mainstream cosmology acknowledges the tension and classifies it as an unresolved measurement problem. Improvements in calibration, better modeling of Cepheid behavior in different stellar environments, or refinements in CMB analysis might close the gap. The standard cosmological model called lambda CDM is stressed but not broken. More data will resolve it. But Adam Riess himself, who won the Nobel Prize in Physics in 2011 for discovering dark energy, has stated publicly that the Hubble tension is not a measurement error. It is new physics. The question is what kind? One deeply unsettling possibility is that the universe is not uniform. Our galaxy may sit inside a region of slightly lower than average density, a structure researchers at the University of Hawaii identified in 2023 as the local hole. If we occupy a cosmic void, local gravity is weaker, local expansion appears faster, and every distance and age measurement we have ever made of the nearby universe carries a systematic bias we have not corrected for. This would violate the Copernican principle, the foundational assumption of modern cosmology that we occupy no special or privileged position in the cosmos. Nearly everything in cosmology is built on this assumption. If it is false not because of arrogance but because of our literal location in space, then the age of the universe, the rate of its expansion, and the large-scale structure we have mapped for decades may all be distorted by where we happen to stand. This possibility is discussed in seminars. It is published in papers. It does not appear in NASA press releases or summary documents for the public. Because if we are special, if our position makes the universe look different to us than to any other observer in existence, then the confident decades of cosmological claims rest on a geography problem no one has corrected. From the broken ruler of cosmic expansion, we descend to a deeper problem. What happens when the universe's own record of the past begins to erase itself? Are we living inside a cosmic void that makes every cosmological measurement unreliable? If the Hubble tension requires new physics, which physics and what else does it invalidate? And if the Copernican principle is wrong, which of our conclusions about the origin and age of time can we still trust? Number 4. Black holes are erasing the past, and physics cannot agree whether time survives. Stephen Hawking spent 40 years at war over a question that sounds abstract but isn't. When something falls into a black hole, does the universe remember that it existed? In 2004, in front of an audience in Dublin, Hawking conceded the argument. He said black holes do not destroy information. He even paid a forfeit to physicist John Preskill, a baseball encyclopedia, symbolizing that information is always recoverable. He was wrong to concede. The debate since has grown darker, not quieter, and the question at its center is whether the past itself can be permanently deleted. If black holes destroy information, they destroy the chain of cause and effect that defines time. Physics does not currently have a confirmed answer to whether they do. Hawking radiation was proposed by Stephen Hawking in 1974. Quantum mechanics predicts that particle-antiparticle pairs form constantly at the edge of a black hole's event horizon. One particle falls in, one escapes as radiation. Over vast timescales, the black hole loses mass and eventually evaporates. The radiation that escapes carries no record of what fell, in only a featureless thermal spectrum. The information paradox arises because quantum mechanics has a foundational rule. Information cannot be destroyed. Everything that has ever fallen into a black hole must be recoverable in principle from the outgoing radiation, or quantum mechanics is wrong. The firewall paradox, published in 2012 by Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS, showed that if information is preserved in Hawking radiation, the event horizon must be a wall of high-energy radiation that annihilates anything crossing it. This directly contradicts general relativity, which predicts that an observer crossing a stellar mass black hole's horizon would notice nothing unusual. Juan Maldacina's AD-CFT correspondence from 1997 proposes that information is preserved holographically, encoded on the horizon's surface. No Hawking radiation has ever been experimentally detected. Modern physics has largely adopted Maldacina's holographic resolution. Information is preserved, just impossibly scrambled in the outgoing radiation. The firewall may be an artifact of incorrect assumptions. Black holes evaporate, the record comes back, the universe remembers. The mathematics is elegant, the problem is managed. But no one has detected Hawking radiation. The holographic principle works in equations and has never been tested in any physical system matching the conditions it describes. The firewall paradox is not resolved. It is navigated by choosing which principle to sacrifice, quantum mechanics or general relativity. Different physicists make different choices, and the version that keeps physicists awake is this. If the firewall is real, every particle that has ever crossed every event horizon in the history of the universe has been annihilated at that boundary. Not slowed, not encoded, annihilated. The past, those particles carry every star that fell into a galactic core, every configuration of matter that ever crossed the threshold is gone. If Hawking radiation scrambles the record beyond any recovery, the distinction between information preserved and information destroyed becomes operationally meaningless. And as the last black holes in the universe evaporate over timescales measured in googles of years, whatever record they hold dissolves with them. Causality, the relationship between before and after that gives time, its direction and meaning evaporates along with the mass. From black holes that may be erasing causality, we move to an experiment that found causality running in the wrong direction entirely. If information is truly preserved in Hawking radiation, does the universe maintain a perfect quantum record of every event that has ever occurred? If the firewall is real, what has it already destroyed at the horizon of every black hole in history? And what remains of time is a meaningful concept when the last black hole has evaporated and taken its record with it? Number 5. The experiment that proved the future can change the past. A photon travels through a double slit. It creates an interference pattern on a detector, the unmistakable signature of a wave passing through both slits simultaneously. Then, after the photon has already passed through the slits and struck the detector, you change the setup to measure which slit it went through. According to quantum mechanics, this choice you make after the fact should change which path the photon took before the fact. In 1978, physicist John Wheeler called this the delayed choice experiment and described it as theoretical. In 2007, physicists ran it with real photons and published the result in Science. The future changed the past. That is not a metaphor. Wheeler's delayed choice thought experiment was theorized in 1978. Experimental confirmation came from V. Jacques, O. Wu, F. Groshans, F. Trisart, P. Grangier, A. Aspect, and G. F. Roch, published in Science in 2007. Setup. A photon is fired at a beam splitter. Classically, it takes one path or the other. Quantum mechanically, it takes both simultaneously. After the photon has already passed the beam splitter, the experimenter chooses whether to detect which path was taken. When the experimenter measures the path, the photon behaves as if it only ever took one path from the beginning. When the experimenter does not measure, The photon produces an interference pattern both paths taken. The quantum eraser variant, published by Kim, Yu, Kulik, Shi, and Scully in 2000, extended this further. Erasing information about which path was taken after the photon has already been detected restores the interference pattern. A decision made after the measurement changes what the measurement shows. Yakir Aharonov and Lev Vaidman proposed the two-state vector formalism in the 1990s. Every quantum particle has both a forward-evolving and a backward-evolving quantum state, a mathematical structure that naturally accommodates backward causation. Hugh Price at Cambridge and Ken Wharton at San Jose State University have published retrocausal models of quantum mechanics in peer-reviewed journals, arguing that backward-in-time influences resolve interpretive problems standard quantum mechanics cannot. Mainstream physics does not endorse retrocausality. The standard interpretation holds that quantum particles have no definite properties until measured, so there is no backward causation, only apparent backward correlation. The many worlds interpretation removes the problem by branching reality at every measurement. No information travels backward in time. But the experiment does not care about interpretation. The data shows that the pattern of photon arrivals changes based on a choice made after the photons have already arrived. Whatever philosophical construction physics uses to avoid the word retrocausality, the numbers require that something is correlating across time in a direction running counter to the arrow. Price at Cambridge and Wharton at San Jose State are not fringe theorists. Their work is peer-reviewed and mathematically consistent with the experimental results. What makes this career-limiting to publish on strongly is not the evidence. It is the implication. If future measurements influence past quantum states, then the arrow of time is not a law. It is a statistical tendency. At the fundamental level, the universe does not know which direction time flows. It solves its equations in both directions simultaneously. The reason we experience time moving forward is not that physics demands it, it is that entropy happens to increase in the direction we call future. And entropy is a large-scale statistical average. At the quantum level, no such preference exists. The future is already in contact with the past. What is suppressed is not the experiment. It is the implication that this contact has no known boundary. Why does the scientific community work so hard to avoid the word retrocausality when the experiments demonstrably show backward time correlations? What does it mean for the past if choices you make today are already encoded in events that happened yesterday? And if retrocausality operates at the quantum level, at what scale does it stop, or does it stop at all? Number 6. There is a hole in the universe that shouldn't exist, and something may be causing it from outside. Map the oldest light in the universe. Scan every direction. Expect near-perfect uniformity. The cosmic microwave background, the thermal afterglow of the Big Bang, should look essentially the same in every direction, to better than 1 part in 100,000. In 2004, the team working with NASA's WMAP satellite found an exception. A region of sky in the direction of the constellation Eridanus, 1.8 billion light-years across, that is 70 microkelvin colder than everything surrounding it. 70 microkelvin sounds negligible. In the near-perfectly uniform landscape of the early universe, it is a scar. And in 2015, when astronomers looked for what was behind it, they found 10,000 galaxies missing. The official explanation is a supervoid. The numbers don't work. The WMAP cold spot was detected and published in the Astrophysical Journal in 2004 by Patricio Vielva, Enrique Martinez Gonzalez, Rafael Barrero, Josep Sanz, and Licia Verde. Istvan Sapudi and his team at the University of Hawaii confirmed in 2015 that a supervoid exists at the cold spot's location. Spanning approximately 1.8 billion light-years, with galaxy density roughly 20% below the cosmic average. An estimated 10,000 galaxies are absent from that region, compared to what standard cosmological models predict. The cold spot has been confirmed as statistically significant at greater than 3 sigma by multiple independent analyses. The integrated Sachs-Wolf effect, the mechanism by which light crossing a low-density region loses energy, is the mainstream explanation. But the supervoid accounts for only a fraction of the observed temperature deficit. The remaining anomaly requires additional physics. Laura Mersini Houghton, a theoretical physicist at the University of North Carolina, published a prediction in 2006, arguing that quantum entanglement between our universe and a neighboring universe in a multiverse could produce exactly this kind of imprint on our cosmic microwave background. She made the prediction before the supervoid was confirmed. The supervoid's existence is consistent with her model. Mainstream cosmology accepts the supervoid explanation with reservations. Voids produce cold spots. The supervoid is real. Better measurements will account for the remaining discrepancy. The multiverse hypothesis is speculative and cannot be tested. Move along. But Mersini-Houghton's prediction is published, peer-reviewed, and has not been refuted on mathematical grounds. What it has been is set aside without engagement. Because if another universe is pressing against ours, leaving a gravitational imprint in the oldest light we can observe, then the word universe no longer means what cosmology uses it to mean. There is no isolated beginning of time for our cosmos. There is only a local beginning, one bubble of space-time among an uncountable number, each with its own initial conditions, its own direction of time, its own physics. Everything cosmology says about the first moment, the initial singularity, the conditions that set all subsequent physics in motion, applies only to our bubble. Something existed beside it, before it, pressing against it. And the scientific community does not discuss this possibility in public-facing communications because it has no framework for what the origin of time means if time was already happening somewhere else. The cold spot sits in our sky. The supervoid confirms a real structure. The deficit remains unexplained. And the most mathematically coherent alternative that something outside is pushing in is career-limiting to pursue publicly. From a bruise left by something outside our universe, we turn to a silence that implies something even more disturbing about what happens inside it. What is causing the temperature deficit that the supervoid alone cannot explain? If Mersini-Houghton's multiverse prediction is correct, what does it mean for the Big Bang as the origin of time? And what else, pressing against our universe from outside, might be shaping the physics we have always mistaken for fundamental law? Number 7. The absence of time travelers is the most terrifying fact in the universe. In 1950, physicist Enrico Fermi sat down to lunch at Los Alamos National Laboratory and asked a simple question. The universe is billions of years old. Intelligent life has had billions of years to emerge and develop. Where is everybody? The Fermi paradox. But there is a version of this paradox that almost never makes it into public scientific discourse, and it is far more disturbing than the original. If even one technological civilization in the history of the universe ever developed travel to the past, that civilization could visit every moment in history. Not a few moments. Every moment in all of recorded and unrecorded time. We would detect visitors from the future the way we detect oxygen. Everywhere, always, impossible to miss. We detect nothing, and the scientific community is very careful about what it says that silence means. The Fermi paradox was articulated by Enrico Fermi in 1950 and formally published by Michael Hart in the Quarterly Journal of the Royal Astronomical Society in 1975. The observable universe contains an estimated 2 trillion galaxies, each averaging roughly 100 billion stars, with current estimates placing the number of potentially habitable planets at 10 billion trillion. SETI, the search for extraterrestrial intelligence, has monitored radio frequencies since 1960 with no confirmed signal. General relativity permits closed time-like curves, closed loops in spacetime, allowing an observer to travel to an earlier point in their own timeline. Kurt Gödel showed in 1949 that a rotating universe solution to Einstein's field equations allows such paths. Traversable wormhole theory, explored by Kip Thorne and collaborators in 1988, permits similar travel in principle. Igor Novikov's self-consistency principle, developed in the 1980s, argues that any timeline permitting time travel must be self-consistent. The past can only become what it already was. Stephen Hawking proposed the chronology protection conjecture in 1992, arguing that quantum effects, at the scale where closed time-like curves would form, prevent them from doing so. In his 2010 revised edition of A Brief History of Time, Hawking cited the absence of time tourists as the strongest empirical argument that backward time travel is impossible. A 2013 study by researchers at Michigan Technological University searched public online archives for information that could only have originated in the future. They found nothing. Mainstream physics accepts Hawking's chronology protection conjecture as the most likely resolution. Quantum effects prevent closed time-like curves from forming. The absence of time travelers confirms the impossibility of the technology. No further public discussion required. But Hawking framed this as reassurance. Read it again. The absence of time travelers has exactly two explanations, and the conjecture only eliminates one. Either the physics of backward time travel is impossible and will remain permanently beyond any civilization's reach, or it is theoretically achievable, but no civilization in the entire history of the universe has ever survived long enough, advanced far enough, and remained intact long enough to build it. Not one. In 13.8 billion years, across 2 trillion galaxies. The second option is a statistical statement about the ceiling that intelligent life consistently reaches before it destroys itself or is destroyed. It is a statement about our probable future as much as about any civilization that came before. SETI discusses the silence in terms of radio signals, interstellar distances, and the rarity of complex life. It does not discuss the time travel Fermi variant publicly. It does not ask, in press releases or public briefings, what the absence of temporal visitors implies about the fate of every technological civilization that has ever arisen in the observable universe, including the one producing this video. Hawking called the absence of time tourists the strongest argument he knew against time travel. He said it to reassure us. Why does SETI avoid public discussion of the time travel Fermi variant? Does the absence of time travelers prove that backward time travel is physically impossible, or that our future contains no civilization capable of achieving it? And which of those two possibilities is more terrifying to sit with? Number 8. Time is pixelated, and no one will say who set the resolution. Hold a phone screen close to your eye, close enough to see the individual pixels' discrete points of light with no information between them. The image looks smooth from a distance. It isn't. Now consider this. Time works the same way. At 5.3, 9 times 10, to the negative 44 seconds, the Planck time, the concept of before and after, ceases to have physical meaning. Below this threshold, no measurement is possible, no interaction can occur, and the universe has no resolution. The mainstream calls this a calculational limit. But something set that limit. Something defined the frame rate of reality. And physics will not say what that something is, because answering the question changes what kind of question it is. Planck time is derived from 3 fundamental constants: the speed of light, Planck's constant, and Newton's gravitational constant. At 5.3 9 times 10 to the negative 44 seconds, it marks the scale at which quantum gravitational effects dominate, and every current framework breaks down. Below Planck time, general relativity fails, quantum mechanics fails. No physical description is available. Loop quantum gravity, developed by Carlo Rovelli and Lee Smolin, beginning in the 1980s, proposes that spacetime itself is quantized at this scale, composed of discrete, indivisible volumes called spin foam, a granular structure beneath the apparent continuity of space and time. The Fermi Gamma Ray Space Telescope in 2009 tested for this granularity by measuring the arrival times of photons from a gamma ray burst 7.3 billion light-years away. If space-time is grainy, high-energy photons should arrive fractionally later than low-energy ones. The photons arrive simultaneously, either ruling out some granularity models or showing our instruments are too coarse to detect the effect. Richard Feynman and John Wheeler proposed spacetime foam. Below the Planck scale, spacetime bubbles and fluctuates chaotically, and the smooth geometry of general relativity is a statistical average over that turbulence. Nick Bostrom of Oxford formalized the simulation hypothesis in a 2003 paper in the Philosophical Quarterly, presenting the mathematical argument that at least one of 3 conditions must be true, the most unsettling being that we live in a computational simulation run by a post-human civilization. Silas Bean and collaborators published a paper in 2012 suggesting that lattice QCD, a technique where spacetime is discretized on a computational grid for particle physics calculations, might produce measurable artifacts analogous to what a universe running on a discrete substrate would show. Mainstream physics treats Planck time as a calculational limit, not a philosophical statement. Loop quantum gravity is an active research program with no confirmed experimental predictions. The simulation hypothesis is a philosophical thought experiment. The Fermi gamma ray result constrained some Planck scale models, nothing to discuss publicly. But the mathematics does not require this restraint, and the suppression is not about the evidence, it is about where the evidence points. If time is quantized, the universe advances in discrete ticks. Every law, every measurement, every moment you have ever experienced is a sequence of frames, each 10 to the negative 44 seconds long. And if time has a tick rate, something determined that rate. The simulation hypothesis is avoided in serious public physics, not because it is mathematically implausible. Bostrom's paper has been cited over 1,500 times, but because if it is true, the question of who runs the simulation, what exists outside it, and whether the timeline can be edited from outside, is no longer philosophy. It becomes physics. And physics has no tools for questions that operate outside its own rule set, because its rule set is what the simulation defines. Why does time have a minimum unit at all, and what physical principle explains why it is precisely 5.39 times 10 to the negative 44 seconds rather than any other value? What would it mean for causality if Planck time represents a computational time step? And if reality has a resolution limit set by something external to it, what is that external something observing when it watches the simulation run? Number 9. The universe is accelerating toward an end that will shred the fabric of time. In 1998, two teams of astronomers were using exploding stars to measure how fast the universe is expanding. Type 1. A supernovae burn with a consistent brightness, the best standard candle in cosmology. Both teams expected to find the expansion slowing down. Gravity should be winning. Instead, both teams found the opposite. The universe is not just expanding. It is accelerating. Something is pushing galaxies apart faster and faster with every passing billion years, and it is winning against every force that should oppose it. Saul Perlmutter, Brian Schmidt, and Adam Riess received the Nobel Prize in Physics in 2011 for this discovery. What the Nobel Prize ceremony did not announce plainly is that the discovery comes with an end date attached, and the end date involves the destruction of time as a physical structure. The accelerating expansion is attributed to dark energy, a property of space itself that exerts a repulsive effect opposing gravity. Dark energy constitutes approximately 68% of the total energy content of the universe. Dark matter makes up approximately 27%. All ordinary matter, every star, planet, galaxy, gas cloud, and black hole that has ever existed, accounts for approximately 5% of everything. Dark energy's density appears constant, even as the universe expands, meaning more space produces more dark energy, rather than diluting it. This violates the energy conservation law that governs every other physical system known to science. Einstein introduced the cosmological constant in 1917, later called it his greatest blunder, and watched it be reinstated by the 1998 data. Robert Caldwell of Dartmouth College published the Big Rip scenario in 2003. If dark energy strengthens over time rather than remaining constant, a variant called phantom energy, its repulsive force eventually overcomes every binding force in existence. The sequence. Galaxy clusters separate, then individual galaxies, then solar systems, then planets, then molecules, then individual atoms, then the nucleus of each atom, then the fabric of spacetime itself tears apart in approximately 22 billion years. Even under constant dark energy, in 200 billion years, all galaxies beyond our local group will have accelerated beyond the observable horizon, permanently, beyond any contact, observation, or signal. Mainstream cosmology accepts the Big Rip as a legitimate but unconfirmed scenario. Current data is consistent with a constant cosmological constant, not strengthening phantom energy. The timescales involved are so vast, they have no relevance to present physics or any practical human concern. The practical fate of the universe remains open. But here is what the press releases omit. Dark energy violates conservation of energy. As the universe expands, matter and radiation dilute. Dark energy does not. We have named a thing we cannot identify, confirmed it constitutes 68% of everything that exists, and accepted it into the standard model with no physical mechanism proposed. The universe is mostly made of something for which there is no theory, and that something is winning. The Big Rip does not merely end life and matter. If phantom energy tears spacetime, the physical fabric that gives before and after their meaning, then time does not slow towards some cold, dark, final moment. The framework that defines sequence, cause, and effect is shredded along with the last atom. What remains is not a universe at absolute zero. It is the absence of any substrate on which temperature, sequence, or time could be defined. From the shredding of spacetime, we descend to a quieter destruction, the one thermodynamics has been warning about since 1865, the one that is already underway. What is dark energy? What physical entity or property does it correspond to? Why does its density remain constant or increase as the universe expands, violating energy conservation for the only substance known to do so? And if the Big Rip tears spacetime itself, is that the literal end of time as a physical structure, not a metaphor, but the destruction of the substrate time requires to exist? Number 10. Time exists because entropy is increasing. When entropy stops, time stops. The universe began in a state of extraordinarily low entropy. Every particle compressed into a point smaller than a proton, arranged with a precision that has no natural explanation. Since that moment, the universe has been spreading that order into disorder, and it will keep doing so until nothing ordered remains. In 10 to the power of 100 years, a number called a googol, the last black hole will finish evaporating. No stars will burn. No atoms will bond. No process will be distinguishable from any other. The universe will have reached maximum entropy, and time, as a meaningful concept, will not slow. It will end. This is not a speculative cosmological scenario. This is where thermodynamics has always been pointing, and the scientific community is very careful about how loudly it says what follows from it. The second law of thermodynamics, formulated by Rudolf Clausius in 1865, states that entropy in an isolated system always increases or remains constant. The universe is the only truly isolated system. Grand unified theories predict proton decay in approximately 10 to the 34th years, not yet experimentally confirmed. Black holes evaporate via Hawking radiation on timescales of approximately 10 to the 100 years. After the last black hole evaporates, the universe contains only expanding quantum vacuum and stray photons. Henri Poincare's recurrence theorem from 1890 shows that a finite system will eventually recreate any prior configuration by chance. But the recurrence time is 10 to the power of 10 to the power of 120 years, a number that dwarfs the current age of the universe by more orders of magnitude than the current age dwarfs a single Planck time. Boltzmann brains's self-aware structures that momentarily fluctuate into existence from quantum noise are statistically more probable in a high-entropy universe than human-like civilizations with consistent memories and coherent histories. Sean Carroll of the California Institute of Technology has argued publicly that the low-entropy initial state of the universe is the deepest unsolved problem in all of physics. Julian Barber, in his second 1020 book, The Janus Point, argued that time is not fundamental, it is a statistical measure of entropy's directionality. The name we give to the direction entropy is moving. Mainstream cosmology accepts heat death as the most probable long-term fate of the universe, notes the timescales as irrelevant to present physics, and classifies the low-entropy initial state as a deep open question. Barber and Carroll represent serious ongoing research. The problem is acknowledged, but here is what the acknowledgement leaves out. If Barber is right, if time is entropy's arrow given a name, then when entropy stops changing, time does not decelerate. There is no after heat death, not a cold, dark after. No after at all. Because after requires a sequence requires entropy moving in a direction. And entropy moving in a direction requires a universe that began far from equilibrium. And this raises the question Carroll calls the most disturbing in all of physics. Why did the universe begin in such an improbably ordered state? The probability of the Big Bang's initial conditions arising by chance is less than 10 to the negative power of 10 to the 123. That number is so small it has no physical analogy. It did not arise by chance. It required something. We have no theory for what that something was, because no physics exists outside time, and time did not exist before those initial conditions were set. We live between two walls. At one end, a beginning that cannot be explained by any framework that operates inside time. At the other, an end where time ceases to be a framework at all. And the scientific community is very precise about which of these it discusses in public, and which it leaves in the seminar rooms. From a star older than the universe to GPS corrections that prove time is unequal. From two expansion rates that should be identical to black holes erasing causality. From photons that change their past based on future choices to avoid that may be a bruise left by another universe pressing against ours. These are not isolated anomalies awaiting better instruments. They are data points arranged around the same outline, pointing at the same gap between what the evidence shows and what the public is told. The gap exists. It has always existed. And the question worth asking is not whether scientists know more than they say. It is whether the full picture, if stated plainly, would leave any of us more comfortable than the version we have been given. What is so disturbing about the low entropy beginning of the universe that Carroll calls it the PAT, the deepest problem in all of physics, and why is it absent from every introductory cosmology course? If time is entropy's arrow, what was happening before the Big Bang set that arrow pointing forward? And if the end of time is already written in the second law, should we be more frightened by the ending or by the beginning we cannot explain? Subscribe and leave a comment below telling us which of these 10 facts unsettles you most. And if you're watching from somewhere very far in the future, you already know how this ends.